Hello everybody, welcome back to Drunk Physics. So last night I kind of quickly compiled a little primer to this lecture that I'm going to do today. So what I want to talk about is the idea of qubits. Okay, so I want to start the talk on quantum mechanics by looking at applications in computation. So we have computational quantum mechanics. That's kind of the field I'm starting to study, and I want to do things with it, obviously. But it's what got me able to understand quantum mechanics in a sort of discrete, kind of coin flip mentality way of thinking about things. You have something, you do an operation on it, and then it immediately changes. And it's a good way to think about it, but it's not really the whole picture. But it's a good way to start. So I'm going to introduce this idea of a qubit. So first of all, we have the idea that you can have states, okay? You can have a superposition of states, and you can have the states added to each other, all right? So, pretty easy to think of. So you have a probability of all of these states looking the same, and they all add up to 1, which means it's 100% probable. So you have this A0 term here, these are, and B1 terms, so you have some amplitude of this term added to some amplitude of this term, and it makes your whole wave function, okay? And a wave function can really be taken to mean anything you like. There's all kinds of different waves and wave types and the way waves add together. I've shown this in some other videos on waves, but it's going to kind of congeal, I think, here into an idea of like operations, individual discrete operations. So we know that the standard bit has only 2 discrete options. You have on or off. So you have an excited state or you have the ground state. So that kind of brings us to the idea of Bloch sphere, because we have a completely different way of thinking about it now. So we're going to consider the qubit as an idea in space. So you have this state here where you have 0 or 1. Okay, those are your ground state or your excited states. Either the electron is up or down, on or off, it's binary, 1 and 0. And it makes it easy to think about in terms of 1s and 0s, but not so easy to think about otherwise. And that's why we move into the idea of the qubit. And the qubit takes any range of, between 1 and 0 states, so 0 plus 1 over 2, or it could be 0 minus 1 over root 2, But this root 2 is an important thing to think about, because that also gives you, it's directly between those 2 states, all right? They're both, it's in the same state at once. It's both up and down. Now, that's one of the weirdest bits about quantum mechanics, is that a bit can be on and off at the same time until it passes through a filter. So, I mean, it's not that they are that way inherently, kind of hard to say out loud, but you're thinking about it as it's there, and it's I had to find my little pen tool, so I got this nifty thing over here. I'm gonna start drawing on this a little bit. So when you have this state up, all right, that's your 0 vector, right? And we use this special notation it's called Durkn notation, where you just kind of have this state. But it can also kind of be not either 0 or 1, but a little more leaning towards 1. So, you have your parallel here. I didn't draw a very good parallel line, so we'll go straight across. That's about as straight as we can get. Now it's a little more 1 than 0. You're starting to get this idea in your head. But the thing is, we can also do this in free space. We can just hold on to it, and we can do it in every direction. So you have this slightly more z, slightly more y, slightly more x, because when you have a ball in space, you can flip the ball upside down, or you can flip it around like this, or you can flip it around on any axis you like, rotating it in space. So then you can say that this point here is on this Bloch sphere. Bloch sphere, I want to say Bloch, like anyway, it's a mathematical picturing of kind of how this whole idea works. Okay. So then we can think of it as an electron rotating in 3 dimensions. But we have this, I took this from a lecture I was watching before. We have this ground state here. And we have an excited state, and that's the way you can think about it, is first of all, just having an on or off state. So we can start using this with classical computing and classical bits to start looking at how that feels to use it. So we have this idea of on and off properties. So we have this A plus B1, and it exists in some state between, you have A amount of 0 and B amount of 1, so you can have 0 of 1 and 1 of 0, or you can have 1 of 0 and 0 of 1, or you can have anywhere you like in between. So we're going to start thinking about this in terms of matrices and vectors. But first I want to talk about superposition, because this is it's another special state. So this here, we're going to draw a little box around this. Okay. Now you have this idea where now you have 2. So it's not just 0, it's double 0. That means you have, 2 states that are overlapping and entangled. And so it's either going to be partially up, and then the other one's going to also be partially up, or they're both going to be partially down, or anywhere in the middle. So they're both like this, drawing really crooked, crappy arrows because I have this touchpad keyboard that doesn't really do what I want it to do a lot of the time. Now we have this idea of ket vector, but what's a bra and a ket? I think I introduced this to you before in the previous video, but we're really going to expand on it now. We have this idea of vectors and states and matrices. So we're going to look at it. The uncertainty principle. It's another guiding principle here, is that you can't really tell if your momentum or velocity. That's not really what I wanted to bring here, but I thought it was a nice little thing to add in. I just kind of want to explain this equation real quick. So delta x, delta rho, and so x and p, they use chi and rho for whatever reason. H bar over 2. So you cannot your uncertainty in your momentum and position measurements cannot be less than h bar over 2. Pretty simple stuff. You can't tell where both of these are. You can't tell both of these at the same time. When you multiply them together, they have to be greater than or equal to this. This is your limit on knowing, both of these objects at the same time. Now you can measure, one as well as you like, but you're not going to be able to tell anything. You're going to lose all of your information about, where it was going once you figure out where it is. It's pretty self-explanatory there. And on the other side of that same coin, you lose all information about where it was when you figure out where it's trying to go, because obviously you're never going to see where it is if you're measuring where it's going. So it kind of blows your mind for a little while, but it's not that important in this particular talk. So we have this idea of vectors, okay? So these ket vectors, well, what do these things actually look like if you draw them out? Because obviously you can't really do much math with these the way they look. Well, we said before that these ket vectors are going to be elements of the complex plane. So all of these numbers here, A1, A2, A3, B1, B2, B3, you can sum them up, but you're doing operations on complex numbers. You're not just limited to real numbers anymore. You can use imaginary numbers, and you can use complex numbers as well. That's not really important here either. What we're going to do is we're just going to play with real numbers in 2 dimensions. But we also, remember, have this idea of a matrix, okay? So we're going to limit ourselves to this little block down here. Okay. Well, actually, it'd be more like the M11122122. Okay, so we're going to limit ourselves to 2 dimensions. Why I want to? Okay. Point is, we're going to move on. Now we're going to focus on two directions, x and y. So that defines our flip operator as, or our x operator here, our x ket vector as 1, 0. So the top number is your x direction and your bottom number is your y direction. So pretty simple stuff. And this isn't going to take much longer. I just kind of want to overview of this and just kind of show how it can work. So we can start now building, the sums of these vectors. So if you add x and y together, then you have a superposition of states where x and y are both 1. So on a circle, that would look like, well, I think I have a little space here. So let's draw a circle. Crappy circle. So you have 1, and then you have 0 going down that way. So if they're both 1 and 0, then that means then they're up here. So you have 1, 1. And that works, but not really, because they're not normalized. So that's why you have this, on the unit circle, you're going to have, when they're both activated, you're going to have this 1 over root 2 plus 1 over root 2. I think I did that right. You guys scroll up and look. So yeah, that's where you end up getting that 1 over root 2, because when you multiply, when you square that number, it becomes 1 over 2. So it becomes half. So when you square 1 squared over root 2 squared becomes 1 squared over root 2 squared is 1 over 2. Okay. So then you have half probability of both. But you can still just play with this even without having to use the square roots and everything, just by kind of making a little flip operator. So what we're going to do here is we're going to take everything that's going on in the y direction and we're going to flip it over. So we take this matrix here, this is the identity matrix. If I were to apply the identity matrix to 0, 1, then I would return with 0, 1. But in this case, what it does is it applies a negative y to it. All right. Then similarly, we can make it we can flip the whole thing over across the origin, and then it becomes negative 1, but still operates on this. So now it's more like negative, and then we take this negative out, and then it's just that. Okay, so when you make both of these numbers here in the identity operation, it becomes negative I. So whatever I is over here, it becomes a negative value of it. So similarly, we can just go here and we can play with this same operator, but we're going to put it on 1, 1, which is not real. But then you just replace it, and now it's negative 1, 1. But what if we take out the y term and make that 0? Well, that's still pretty simple, and then it just becomes 1, 0. But now we apply your y operator only to y. So now we're applying y to x, which doesn't actually do anything. That shouldn't have been there the whole time, but now we got this negative 1 here. Well, we don't, actually, because we didn't do anything to the x direction. So it multiplies across to this 1. So this 1 affects, here, let's get out the tool, okay? All right, so this 1 here affects this 1. All right, so it's like an identity operator. All right, so it keeps this 1, but it makes negative 0 across the bottom here. So this row hits that part of the column, and then it makes negative 0, which is still 0. It doesn't really make any difference. So now let's play with it again. Well, let's do one more thing. What happens if we go and we go 1, 0? And then we're going to turn both of these on. Oh, what I just did is I multiplied the 0 by the 1 down here, so it's still the same thing. What if I do it to a 1? So I make this 0. There we go. And now we apply it. So now it multiplies across the first, and now it just turns this one off. Okay. That's basic, coin flipping type of thinking for, turning on and off states. But Quantum computing goes much deeper into this. It says there's now 3 states you can work with. You can go in the X, Y, and Z spin components, and then you can flip those around or kind of couple them so it's kind of spinning, in both the X and Y directions. And then you can feed them through filters like these operators here. Think of this operator like a machine you just throw an electron through. So whatever this electron was in the first place, it's just going to change it to whatever this machine does to it. In this case, it's going to turn, right, that wasn't right this whole time. So yeah, you got this 0, 1 across this 1, and it turns it off. Well, now you can just turn everything off. Now it just turns it both into 0. Okay. You might be asking what these guys do, but I think they make an effect on the opposite one. It's like shear. I'd have to play with it a little longer or write it out. I don't feel like doing that right now. We've already kind of gone over the 15 minutes I wanted to be with here. But I mean, this is as simple as it really gets with quantum mechanics. You get this idea of coin flips, and you can start thinking there, and then there's a lot more to learn. So again, if you like what you hear, buy me a beer. Like and subscribe to my channel, please. You guys are my customer base. You guys pretty much make sure that I get the views I need to get the money I need. So, and if also you like this whole thing I got going, I got my own Patreon account too. And that's www.patreon.com/nakedfoollotus. And that's my Patreon account. If you feel like buying me a beer once a month or something like that, just kind of keep the love coming, man. I do this stuff for free, and I don't want to do it for free. I don't really want to do this anymore because I'm not getting anything out of it. I mean, I do it for the love of science, but sometimes, just the cost becomes outweighing the benefits. So, thank you again for watching, and thank you for tuning in. This has been another episode of Drunk Physics.